Hey everybody, this morning I thought we would start looking into some different diagnostic tools and some simple testing that we would use our ohmeter for. In our industry, we mainly are working on clipper blades, clippers, scissors, things along that line. So when we're doing these diagnostics, we're mostly talking about testing the different aspects of a clipper. We could also, the pet groomers and the veterinarians that we work with use dryers along with our agriculture customers. So these are big blowers that have vacuum cleaner motors in them, switches, sometimes heating elements, different things like that. And so all these basic things. I had a call this week and a gentleman was struggling with a clipper and he really had never used his meter before, though he did own one. So that was a good benefit and we were able to help him over the phone. So I thought we would look at, this is a meter that we use here. It's a pretty simple one and it keeps it pretty easy for the beginner because our actual symbols on here that we're going to use, and this one's getting a little old so they're a little faded, but we've got it turned off right now, and this is a digital meter and this one's by Digisnap, and again we don't sell them or anything like that, but this is a nice tool. And it's got a range. We've got different symbols that are in here with our different settings. And the one that we're going to use more than any is all the way at the top, which is our ohm meter. And then we have this next setting down with a solid line and a dotted line. And that is going to be for DC current, for voltage. That's the V. And then we have this with the wavy line, which kind of indicates for the hertz that we think about in our power grid is the wavy. And so that is our AC voltage, like at your wall that you plug into. And then down here we have two different ranges of amperage that we can test. And with this meter, it has a clamp on the top that we can go around and isolate out the neutral wire so we can see what the amperage is. And so we do have an adapter that we plug into the wall, and then we plug the clipper into that, and that gives us the ability to see what kind of amperage we're pulling. So again, I'm going to move us back up here to the top where we have the ohm meter. Now that kind of looks like an upside down horseshoe with two little feet on it. That is our indicator for resistance or ohms. Kind of like the omega symbol, but that's what we're looking for our ohms, our resistance. And when I'm talking about resistance, I'm talking about, is the wire complete or is it broken? And the first thing we're going to do is we're going to test our meter itself. I'm going to prop it up here so we can see this a little better, but right now on my screen it says OL. The gentleman that I talked to on the phone yesterday, on his meter, it right now, without anything touching each other, it said 1. Which means 100% resistance. And sometimes they'll say 100. If you have an analog meter, it's the needle is just going to sit over to the side, indicating also that there's no circuit. Now if I take and touch these together, there's a battery inside obviously because we're turned on, but I'm going to complete a circuit by just touching the two ends of my leads together. And when I do, this meter goes to very close to 0. It's 0.1 right now. And that just gets into the resistance in the wire. But it's also toning. And I don't know if you can hear that in the camera, but it's got a little beeping sound, which is good for me because I'm a little distracted now and then, and I can listen to the tone rather than have to look at the meter. And in this case, we're not really trying to worry about whether or not we have a certain amount of resistance. We just want to know if it's a good wire or a broken wire. And that's what it's going to tell us. And if it's toning, that's telling us it's a pretty good circuit. All right, so I'll use our armature here that we're going to look at in a little bit, and I'll prop that up. My first little prop here that I'm going to pull out is a cord that was on a clipper. How many of you think I need to really do a lot of testing on this particular cord? I mean, here's both ends. The outer insulation's broken. In here we can even see some of the interior conductors saying that this is definitely bad. So I'm really not needing to use my meter at all here. I'm going to use logic, and we're going to just set it aside as bad, and we're going to put a new cord on for the customer. But now in this case, this cord that we're going to have up here, it's a little bit wound up, but this particular cord looks overall in pretty good condition. But the complaint that the customer had is that either the tool didn't turn on or that it was cutting in and out. And so in order to check this, and this is a fun example for today, this is a polarized cord, meaning that the two tabs on the end of the cord, one is narrow and one is wider, thicker. We've all seen that. And it forces you to put it into the outlet on the wall one direction only. Polarization gets into the flow of the electrons coming through the wires coming from the power source. And so our narrow prong is our hot lead. That's where the power is coming in. That's where the voltage is coming into the tool or into the cord to go to the tool. Once it's being used and there's leftover electrons, they're going to come back to the fat tab, back into the circuitry as the neutral. So we have hot and neutral. So we always know that. And by our UL listing standards, the white wire is our neutral and our black wire is our hot wire. So to check that, right now, we're not plugged into the wall. We're just out here using this. And we want to, just like when I touched the leads together and it completed the circuit, now I'm going to put the whole length of the wire in between. So I'm going to touch one end of my lead to our white wire terminal, and then I said the fat wire on the other end, or the fat lead that plugs in the wall, is the other end of our circuit, or our wire. Sorry, I get my hand in there. And right now, that is showing an open line as a broken wire. So that tells us already that we definitely found a bad cord. Now, if I touch the hot wire and I go to the narrow prong, that also is a broken wire. So in this case, we really had a bad cord. Both wires are broken, and it needed to be replaced. So we were able to take care of that. Now, if I can play with this a little bit and see if anything changes. Sometimes we can get a reading, so I'll double check my meter that it's working. Yep, it toned on us. My guess is, and the most common place for wires to break is right here near the strain relief, the part that connects just off of the utensil or appliance that we're going to be working on. And usually where they break is right behind the strain relief, right back here. So most likely those two wires are broken inside right there. All right, so we're going to set that aside. And we're going to look at another idea, and this is just a simple on-off switch. In this case, we can still use our leads to check this. I'm going to put one of my leads off the meter in both sides. And if I have the switch turned off right now, it indicates open line on my meter. When I flip the switch, it shows 0 resistance or 0.1, showing that we do have a good circuit through that switch, and it's a good switch. If I flip the switch and nothing happened, we would know that we had a bad one, and we'd be able to replace it. So those are some simple diagnostic things we can do. Again, I'm trying to play a little bit, but what do you think on this switch? Do I need to do a lot of testing on this one? Obviously this was dropped and the whole toggle was broken off. But we could still test it just to see if it was making contact. So I would go into my two leads on the switch with my two leads on the switch, and it shows open line on our meter. I'll hold that there. If I swing it around a little bit, no, it's definitely broken. So what we saw with our eyes, logic told us that it was broken, and we just proved that that's true. All right. Now, this is a little more of a difficulty for us in our industry, and we're not going to get into fancy testing and oscilloscopes and different things like that. But in a circuit board like this, or PCB, we have multiple apparatus or different things on this board, resistors, a rectifier, a diode, some different pieces like that, along with a contact switch. Then we also have this little piece over here that our cord attaches to. And so that's all soldered together. And when we go to check that, as far as an overall switch, and we're using resistance, and we say, well, here's where the cord goes in, here's where it comes out, and I turn the switch on, sorry, I'm blocking the meter here, I still get no readings. And that's really because the board is separated by all the different components that make up the PCB board. So we could check individual components. We could come in and check this resistor. Again, I'll try to get this around so that we can see the meter change. I get my leads down here on both ends of the resistor, and we get a reading, and it says it's kind of bouncing around a little bit, but 1.4 to 1.6, or 10.1 to 10.6, sorry. And now it's just moving around just a little bit as I'm making contact and whatnot, settling out at 10.2. Now if we were to get a chart, we could read the bands on the resistor, and it would tell us what resistance this resistor was designed for. And that would give us an idea whether or not it was good or not. Typically though, when we go to check this, this is all brown or it's exploded into multiple parts. And we, again, can just use simple logic to know that that board or that resistor is burnt out. And it's actually one of the most common things on this particular circuit board to go wrong. When there's overloading into the circuit board, the resistor really protects the rest of the motor, or in other words, it burns out and everything shuts off. With a circuit board like this, and in this particular case, we could say, wow, we found that it has a bad circuit board. We're just going to put a new circuit board in. That's not the direction to go, for the reason that most likely, the reason that this board is burnt out is because the armature, now again, the armature I'm using to prop things up doesn't fit the same tool, but if this were bad and shorting out internally, it would be putting spikes of voltage that then burn out the resistor. So it's actually the motor's fault that the switch is bad. And if we put a new switch in, we have a little puff of smoke as soon as we plug it in, and we think, wow, look, another bad switch. Now the logic in someone's mind may say, whoa, there's something else wrong here. Let's stop. I will tell you, I've had phone calls where someone has said, now this happens to be an Andis circuit board, and they'll say, gosh, is Andis having a problem with their circuit boards? I've put 7 of them into this clipper, and every time I do, they just go poof. And I have to say, I'm sorry, no, there's not a problem with the circuit boards. You have a shorting problem in your armature. And that high resistance is what's causing the boards to burn out. And it's about $10, $15 a piece. That person spent a lot of money just on replacing boards because it had a bad motor. So what we want to do is we want to check that armature. So we're going to take and set that aside now. And if we look at an armature in general, we have a steel core with copper windings. And those windings are all interconnected and are swedged in underneath these tabs in the back. And this area back here, this piece, is called the commutator. Now when we come in and we check these, we can check in pairs. And we could even, most of these types of motors are going to have carbon brushes, and the carbon brushes kind of insert from the sides. And so we could pretend like we're the set of carbon brushes and touch 2 contacts on each side. My meter timed out and shut off. We're going to turn it back on. We'll test it again. There we go. Maybe we can use our clipper to prop that up a little bit now. And again, I could come in here and just be 180 degrees from each other, touch 2 contacts, and see if I get a reading. Now, what's happening right now is I'm not getting any readings at all. I can also do these in pairs next to each other. So there's a reading, and I could read that as 2.7 ohms. If I jump over 2, we'll see what this one says. We're again at 2.7. We'll go over 2 more, and we're getting a reading at 2.8. Yeah, okay. Keep going. Now we're at 2.8 again. Uh-oh, now we have an open line. Now this right here is telling us that there's a broken wire inside one of these windings, either out here toward the surface that we can see. I don't see the broken wire right now, so it's very possible it's down inside somewhere that the wire has burnt through and broken. I don't see anything very obvious. Sometimes we'll see that broken wire. But right there, once we found an open line, we don't need to test anymore. One of the things I was telling you is how I was getting readings so far around the armature, around 2.7, 2.8. For engineering tolerance, all these windings in pairs need to be within 10% of each other. If we were outside that 10%, and so if we're going around and we're reading 2.7, 2.8, 2.9, 2.5, we're relatively within a few percent of each other. But if suddenly we had one that read 9.6, that's more than doubling that resistance. We know that set of windings is outside the engineering tolerance and the armature would be considered bad. And that's when we would suggest changing that component. Now what that's doing is that high resistance winding, again, is going to be putting heat into the motor. A lot of times a customer is going to feel that or the end user, by having a very hot body right in the area of where that motor's spinning, because this is going to superheat under that extra resistance. So symptom-wise, they'll come in and say, well, it's so hot I can't hang on to it anymore. So it's not hot because the clipper blade is pushing heat back in from friction, but it's because the motor itself is laboring to stay up to speed. And while it's doing that, we're creating and generating heat that is dissipating instead of those extra electrons moving on through efficiently and then going back to the neutral. So those are things that we can look at and we can see. Another thing that we can check when it comes to an armature is if I put my lead on the core, the steel component, and I just come around in a circle real easy, and I touch all the segments all the way around. If I happen to find a circuit, now we know we have and this one did not, by the way, no readings all the way around. But if I did, that would tell us that from the copper winding to the steel core, somewhere the insulation is damaged and they're touching each other, making it, again, have an internal short. So that would be another reason why we would want to replace that armature. So armatures, again, that's how we would test those. Now I want to take and just do a quick example of an actual clipper that's all intact here. Now, as far as we know, this clipper works. I actually have an outlet over here on the wall that I can reach over to. Plug it in, and we'll turn it on and see. Nope, see, this one doesn't work. Gosh, now, what is it that could cause this to not work? Oh, wait, now it turns on. So I don't have a blade on it, that's why it's so loud. Sorry about that extra noise. But I'm not going to leave it plugged in to make sure we're checking things, but that first time it didn't seem to make contact and turn on. That can be as simple as a piece of hair down in the mechanical switch. But in order to test the different components, there's really, on this is an electromagnetic clipper, and with these there's really only ever 3 components that we have to check. So one of those components, and I just took out a screw that holds the switch in, along with the actuator I removed. But we have a cord that we need to check, we have a physical operating simple mechanical switch, and then we have our field coil that is our magnet that gives us our power. When I go inside here, I'm going to unwrap our wires from each other so I can see them better. And there's a white wire down inside from the cord that's also connected to the field through this red wire. Our switch, if you can see here, there's one of our black leads is coming from the cord, the other is the other end of the winding for the field. So what we can do first is we're going to take off the factory tape, and I know that will seem odd to some that with all today's different types of insulators, but at the factory they still use black electrical tape tucked in around the contacts where the cord solders to the switch and the field. So I get those pieces of tape out of the way, and now we can see our contacts here. So this side over here was our black wire coming from the cord, and again this switch had a lead already on it from the factory, and then it was soldered here to the cord. Now I'm going to just go ahead and take our meter again. I'll try to prop it up again like I did before. Maybe we can see those numbers. But again, all I'm going to do is I'm going to test it, make sure that we have good flow. I'll go to our fat wire up here, and I'll find our white wire on this end, and we'll touch it. and it says that we have a good connection. So that wire from where it plugs into the wall all the way up here is good. We're going to do the same thing again with the black wire off the cord. Remember, on our polarization, that's the narrow prong on this end. So I'll get it in there. I'll move out of the way so we can see. I've got both ends, and we have a tiny bit of resistance, but realistically, that's a good circuit, and we can hear it toning. I'll remove our leads again. Now, just like we did before with the simple switch, we have another simple switch here. And all we need to do is touch both sides where the wires go in and come back out. Right now it's off and there's no reading. I'll flip the switch, touch them again, and we have good tone. We have a full circuit. The last component that we have is our winding. The winding is, again, a steel core similar to our armature with a copper wire that's wrapped around a plastic sleeve. And with those two opposing metals, and then we add a power source, we create an electromagnet. So what we're going to do, again, is I'm going to touch where the red wire from the field comes from this side. I'm going to take the other lead on this end here and find a connection. And it shows some fairly decent resistance. Now we have a long wire, but we do have a connection through them. It keeps kind of me, it's how I'm holding things. But we've got 74.5. Now we don't know what the resistance should be on this. We know that the clipper turned on. We know we had that glitch at the very beginning, most likely a piece of hair, or maybe it was even how I had it plugged in the wall. And we got that solved and it's now working. And then we proved that things are working by checking our cord, our switch, and now the armature, or our field, that says that each component has a current that can flow through it. And really, that's what this tool needs. Each of these windings may have slightly different readings based on the copper that was used and how it was wrapped, and then the thickness of insulation. So you can get little variables within that reading. Here we had that 74.5. The next one might be 80. I don't know. But so we're not really concerned about that. We do want to make sure that it has a reading. Those are very simple and basic diagnostics that we can do. And notice that when I'm doing these, I'm not plugged into the wall, so I'm very safe. There's nothing here for me to get electrocuted with. Now, if we had to go to another layer of diagnostics where we needed voltage involved, that'll be for another video, but we will bring that content to you sometime soon. Again, thank you so much for watching. If you liked our content, follow us or put a like, and we really appreciate everybody that's out there. Again, thank you very much. You take care.